Good afternoon, everyone. My name is Collin Tittle, and I am a master's student in the lab of Dr. Chris Backhouse. So our lab is the Applied Miniaturization Lab, and in it we try and take medical diagnostics, which normally require large instruments and full laboratories, and scale them down to something that you could hold in the palm of your hand. So an important technology for doing this is to have a microheater which accurately controls a volume of reagent and can be operated on a low power budget. So in our globally interconnected world, it's important that we can rapidly and cost-effectively diagnose a variety of pathogens and diseases when they're present in our environment. This need of society is slightly contradicted by the normal means of diagnosing a disease, in which we require a full lab and a variety of systems to support the medical diagnostics. This need can be somewhat reached by using lab-on-chip technology, which uses very small systems which are generally more closed than biological laboratories, which prevent systems from disrupting and producing false negatives in your tests. So what we have developed is a microheater which controls your reagents, and you can perform tests like the polymerase chain reaction with. So here we have created a microheater which, there it is. All right, we have created a microheater which is on the back of an aluminum mirror, which allows us to pass current through this area here, creating a thermally controlled region. So this was done using rapid prototyping techniques, which are an important advance which we use in our laboratory work. So traditional lab-on-chip technologies are often using things like glass substrates and lithography techniques to pattern them. We use primarily plastic materials, and we use a laser to blast them, which allows us to remove the step of lithography from it. So when I am creating my microheaters, I can go from an idea that I want to try to testing it in probably the time scale of 15 minutes. Whereas if you want to do a traditional lab-on-chip setup with lithography, you're looking at 5 weeks. So this allows for a more rapid process of design modification and improvement, and also allows us to tailor our heaters to specific needs. So I'm just briefly going to go over our design. So our design is a resistive heating design where we pass current through 2 traces in the aluminum, which heats a well which is above the heater. We've also taken the step of integrating a sensor into our system, which is different from many traditional heating systems which have a thermocouple or some other sensor independent. So we have a sensor located right in the middle, which would be great if my laser worked. There it is. Right here, where we take advantage of the thermal coefficient of resistivity, which is the physical phenomenon where as you heat up a metal, its resistance increases, and you can therefore have a temperature calibration so that if you measure a resistance through your sensor trace, you know exactly the temperature of that trace. So now that I've talked about the design and how our system for making a microheater is different, I'm going to talk about how we applied it. So the polymerase chain reaction is probably one of the most commonly used medical diagnostic tools in the world. And basically what it does is it takes one copy of DNA, and using some enzymes and biochemistry, you can amplify it to hundreds of millions in the time scale of a few hours. To do this, you basically have to have the biochemistry knowledge to mix together the correct reagents, and then you have to thermally cycle that reagent mixture. Well, we have a microheater which we can thermally cycle efficiently with, and I know some people who know a few things about biochemistry, so they gave me that stuff. So I took that, put it into a well, which I milled above the microheater, and I performed PCR using this microheater. So specifically we used we tested for the HFE exon 2 gene, which is a genetic marker for human hemochromatosis, a blood disorder, and is one of the most commonly prescribed genetic diagnostics in the developed world. So this is a picture of my setup. This is a LabJack U6, which is just a controller which we use to regulate the amount of current which we're passing through our microheater. In the middle there is our chip just sticking out on the bottom left side from the chip holder, which we use to regulate the pressure around the chip, and we can also have an LED in there so we can perform spectroscopic measurements and fluorescence measurements on our reagent as the PCR is progressing. And then on the right there we have a spectrometer, an ocean optic spectrometer, which we can connect to that chip holder as well. And then all of this is sitting on my laptop. So this just gives you a scale on as how portable our technology is and the potential feasibility we could have for implementing this in point-of-care applications. So the HFE Exon 2, which we tested for, is 112 base pairs in length when you've fully amplified it. So in the gel electrophoresis image on the right-hand side here, you can see that we have a strong product band right above the 100 base pair marker. This indicates in triplicate that we accurately thermal cycled the PCR mixture and therefore performed successful amplification. We verified this using melt curve analysis, which takes advantage of the relationship between the length of a product and the temperature at which the double-stranded DNA will separate. In this, we can see our predominant peak is at about 81.5 degrees Celsius, which, if you use an equation, you can calculate to being approximately 110 to 112 base pairs in length. So this further supports our evidence of successful PCR. So now that I've talked about our chip design, and I've shown that we can implement this in a PCR reaction, I'm going to briefly discuss how our technology compares with what's currently out there. So this image here is a picture of my chip sitting on top of a Biorad CFX, which is a top-of-the-line standard PCR machine. You can see that our chip is orders of magnitude smaller. I can bring in one of my chips for a demonstration at a talk, whereas I can't pick up a CFX on my own. It's about 21 kilos, whereas our chip in its holder is about 50 grams. So as well, our chip, it's produced on polymer mirror, which you can get from a Home Depot supply store or something like that. And it costs a few bucks to make, as opposed to a Biorad, which is $30,000 up front, and then you have consumables and reagents cost on top of that. So this means that we have a chip design which can be rapidly adjusted and prototyped, and it's fabricated on commercially available, fairly cost-effective polymer mirror. As well, when I was running that PCR with the chip, the power budget is such that I run it off my laptop's power supply. This means that if we want to deploy this technology in point-of-care applications, theoretically you could deploy it with just someone with a laptop powering the entire genetic test. So therefore, this low power requirement and the cost effectiveness of the production chain mean that this could be fairly readily implemented in point-of-care applications in the future. So in the future, we'd like to provide with further integration of this technology with other lab-on-chip systems. So one thought we have is to use sample preparation microfluidics, couple that with the PCR heater, which is then further coupled to a CE system, or capillary electrophoresis, which would allow us to do a complete sample preparation through to fluorescence detection of a specific target. And this would be the case where we would require no human interaction with the system at any stage in between, which is a common location for contamination and which would potentially cause false negatives or something bad like that. As well, the power requirements for this system are such that it could be readily implemented in a CMOS type setting, and then that would provide a pathway for using a microheater like this in a USB key-sized device that a clinician could simply plug into their laptop and perform a test with. So that is my talk. Thank you for listening, and does anyone have any questions?